Okay, hello everyone. Welcome to Module 9. So Module 9 focuses on two laws in magnetism, and they're really the fundamental laws that link magnetism to electricity. So it's sort of now like we're at the part in the course where it's all coming together, and things that you learned at the first part of the course will start to come back as you see the connection between electricity and magnetism. So, how the content is organized in collage is into four different concepts. The first concept is Faraday's law, which there's a video, there's a few videos of like some demos. There's a video of me doing a demo in the Science Center and of me explaining the basics of Faraday's law. And then there's also a couple of like other demo videos that I posted that are interesting. And then this video is going to be on Lenz's law. And then I'm going to make a third video, which I'll post in the third section under motional EMF. And that third video will include concepts 3 and 4. So concept 3 is motional EMF, and it's motional EMF is really the same as these two concepts. It's just there's a slight variation that is introduced. So, but it's basically like the same as Faraday's law and Lenz's law. And then induced E fields is this idea that if you have a changing magnetic field, you induce an E field either in a wire or in the air. And I'll do a bunch in video 3, I'll do a bunch of example problems from those two concepts, and those will be hopefully helpful for your challenge this week. Okay, so let's talk about Lenz's law. So Lenz's law is impossible to disentangle from Faraday's law. Lenz's law is basically just the sign. Like if we go back to what Faraday's law is from the first video, so this is the formula for Faraday's law. This negative sign is Lenz's law. So remember, Faraday's law basically says that when you have a changing magnetic flux, a time varying magnetic flux, you induce an EMF that creates a current. So remember this symbol here stands for EMF, which is electromotive force. And this is just a fancy way of saying voltage. Okay, so we can replace this E induced with just V. So whenever you have a time varying magnetic flux, you induce an EMF or a voltage, and that EMF causes current to flow. Okay, and what Lenz's law says is that that current, the direction of the current, will be in whatever direction it needs to be to oppose the change in flux. Okay, and so that's where the negative comes in. So it's written here. This means that the direction, it's just telling you the direction of the induced EMF that causes the current to flow in whatever direction it needs to oppose the change in flux. Okay, that's basically summarized here. The induced current flows in whatever direction is needed to counteract the change in flux of the original magnetic field. Okay, so we're going to do a bunch of examples that it's like a lot to get your head around. Without examples, it's really impossible to see what this means. So, okay, so we'll start with this example. Suppose we have the north pole of a magnet, and we're moving it towards a loop as shown in this picture. And we want to know what is the direction of the induced current. Okay, so by moving the magnet closer to the loop, we are changing the flux. So let's just review what flux is exactly. So remember, this is the symbol for magnetic flux. Okay, magnetic flux. Okay, and remember, magnetic flux is just the dot product between the magnetic field and the area. Okay, so that's going to be the B field times the area times cosine theta, where theta is the angle between the area vector and the B field. Okay, so remember the area vector is just a vector that is perpendicular to the plane of the loop. So let's see, let me draw the area vector in red. So I always, remember the area vector, like you can draw an area vector pointing in this direction, or you can draw an area vector pointing in this direction. It doesn't matter. It's up to you which direction. The only thing that matters is that it's 90 degrees to the plane of the loop. What I always do when I'm trying to figure out induced current is I always make my area vector in the same direction as the external magnetic field. Okay, so these green lines are the external B field. Okay. Remember, we're gonna have another B field to contend with, an induced B field, as of which comes from the change in flux. Okay, so that's basically what Faraday's law says, right? So Faraday's law says that you have an induced B field that opposes the change in the flux. Okay, and that gives rise to a current. Okay, so the steps in terms of figuring this out is we first have to figure out what is the flux? What's happening to the flux? Okay, so in this case, let me change color. So in this case, the North Pole is getting closer to the loop. And so the flux, the B field is, remember, the B field is going to be stronger here than like here, right? The B field is weaker here. So by moving the magnet closer to the loop, we are increasing the flux. Okay, so the flux is increasing. And it's increasing to the right because that's the direction that the external B field is pointing. So we're going to get an induced, therefore, there's going to be a B field induced that will point left to oppose the change in flux. Okay, so let's make that B field orange. Okay, so this is going to be the induced B field, induced. Okay, and then the final step of this is once you figured out that the induced B field is pointing to the left, is to use your right hand rule, the first right hand rule, where you point your thumb in the direction of the B field and your fingers indicate the direction of the current. Okay, so if I point the thumb of my right hand to the left, my fingers are going to be curling like into the page. Okay, so the current is going to be kind of like going like this, like into the page. It's difficult to draw like on this picture because so like maybe it's better to say like the current, the induced current is going into the page, which is this symbol, right? It's going into the page like above and out of the page below. Okay. So those are the steps. Okay. And it's like this opposition, the opposition of the induced field that is sort of dictated by Lenz's law. So like I said, like this whole formula is Faraday's law. Like the fact that when you have a time varying flux, you get an EMF and that EMF induces a current. And then just the negative, basically the Lenz's law just tells you which direction the current is going in the loop as a result of that induced B field. So this is the general strategy like that I just went through. The first step is to look at the flux, the number of field lines going through the loop. I always set up my area vector pointing in the same direction as the external B field, just so that I don't have to think about a negative flux increasing or decreasing, right? Like by setting your area vector in the same direction as the external B field, you're automatically making the flux positive. And I personally think it's much easier to think of a positive number as getting bigger or smaller than I get confused when I have to think about like a negative flux getting bigger or like it just confuses me. So that's why I always set up my area vector in the same direction as the external B field. So you look at the flux, you figure out what's happening to it, if it's increasing or decreasing, and in which direction. And then you ask yourself, which way does the induced B field need to point in order to get back to the original flux, right? So like if you think of this picture here, the one that we just considered, and the position of the magnet right now, when I move the magnet to the right, the flux gets bigger, right? So you ask yourself, which direction does the induced B field have to point in order for the flux to go back to the way it was? Well, it needs to point to the left because like if I add that B field to the increasing B field that's pointing to the right, that's how you get back to the original. Okay, and then the last step is to curl your fingers in the direction of the induced current once you point your right thumb in the direction of the induced B field. Okay, so there's nothing more to it than that. Like if you follow those four steps, it's the exact same every single time. Okay, so here's three more examples that we'll just go through together. Okay. So in what direction will the current, it's the same question every time. Like what direction will the current flow? Okay. So the first question that we ask are, well, let me first draw the area vector. Okay, so I'm gonna draw the area vector in the same direction as my external B field, which is pointing to the left. And that's simply so that I start out with a positive flux. Okay. So now the first question is to ask yourself is what's happening to the flux? Okay. So the magnet is moving to the left, okay? And remember the strongest part of the magnet is here. So the strongest part of the magnetic field is right, close to the pole. This is like strong and this is weak here. So the flux is decreasing. Okay. Um, and it's decreasing to the left. So which direction does the induced, so like which direction, second question, which direction will be induced be to oppose that change in flux? Okay, that's always the second question you ask yourself. And the answer is to the left, right? Oops, I'm gonna make it orange again. The answer is that the B induced, it's like if it's to the left, I'm like adding more B field lines pointing to the left to counteract the decrease in B field lines that is occurring as a function of me moving the magnet away. So the B induced is to the left to kind of like reinforce the B field that is like dissipating from the magnet moving away. Okay, and so then the last step is always the same. As a result of that B induced, which direction, so which direction does the current flow? Which direction does the current flow? And that's just the right hand rule again. So I'm going to point my thumb in the left hand direction. And so it's going to again be like going like into the page, which again, I find very difficult to draw like this, like to draw on these kinds of diagrams because it's not clear when you look at this circle which part of the loop is in the front and which is in the back, but it's basically going into the page. It's going into the page here and out of the page down there. Okay, another way to look at it is if I was standing, I mean, well, it depends on which side you're standing, as to whether it's counterclockwise or clockwise. But anyway, you get the idea. So it's moving, like this, like my fingers are moving into the page at the top and out of the page at the bottom. Okay. So that's another example. Let's do this one. What direction will the current flow? Same question. If you move the south pole towards the loop. Okay. So first question, what is happening to the flux? Okay. Oh boy. Okay, what's happening to the flux? Okay, so the flux, so I'm moving the magnet towards the loop. Okay, again, I'm going to set up my area vector in this direction. Okay, so I have a positive flux. Okay. So what's happening to the flux? It's increasing, right? The flux is increasing as this part of the magnet gets closer to the loop. Okay, second question. Which direction will be induced be? Be induced. Okay, so remember that's going to be in whatever direction it needs to be to oppose the change in flux. So the change in flux is getting stronger, and it's getting stronger to the left. So B induced is going to be pointing opposite to that, right? So it's going to be pointing to the right. Oh, I did it in red. I should have done it in orange. Whatever. So B induced is going to be pointing in that direction, right? Because it opposes like the direction of the existing B field, which is getting stronger. Okay. And so the last question is always, as a result of that, B induced to the left, which direction is the current? And again, just right hand rule. So I point my thumb to the right. So it's going to be coming out of the page above and then into the page below, right? So like kind of like that. Okay. Okay, last example. Which direction will the current flow if you pull the north pole away from the loop? Okay. So now it's just, I mean, it's all the same, right? Like once you've done a few of these, like it becomes pretty routine. So I put my area vector in the same direction as the B field, so I have a positive flux to start with. And then I'm pulling the magnet away from the loop. So what's happening to the flux? The flux is decreasing. Okay. So which direction is B induced? B induced is going to be in whatever direction it needs to be. So it's to oppose it. So it's going to be pointing this way, right? To reinforce, because it's like the initial B field is pointing to the right, but it's getting weaker. So so that means the B field that's going to be induced will be also pointing to the right to reinforce it. Okay, that's the way I think of it. And then third question is current. So again, I point my thumb to the right. My fingers are going to be coming out of the page at the top into the page at the bottom. It's going to be like this again. Okay. All right. So I think like if you follow those steps every time, area vector pointing in the same direction as the external B field, you ask yourself what's happening to the flux? Is it increasing or decreasing? And in which direction? As a result of that, which direction is the B induced? And then final step, right hand rule, point your thumb in the direction of B induced. Your fingers represent the current. Okay, so like these examples that I've just gone over are basically like a combination of Faraday's law and Lenz's law. Lenz's law, again, only shows you the direction of the induced current as a result of the changing magnetic field. Okay, in this video, I want to do one kind of basic example of using Faraday's law and Lenz's law, and I think this will be useful for the problem set or for the challenge. And then in the next video, I'm just going to do a bunch of different examples that show the concepts in the other two parts of collage. Okay, so let's look at this one. So let's say you have a square loop with sides that have a length of 5 centimeters. The loop is situated at the edge of the uniform magnetic field, and the magnetic field has a strength of 0.6 Tesla, and that is pointing out of the page. Or sorry, into the page with the little X. Okay, as shown. You pull the loop, so you're pulling the loop in this direction. You're applying a force there. And you pull it completely out of the field at a constant speed during over a time of 0.1 seconds. Okay, so what we want to know first is the initial magnetic flux and the final magnetic flux through the loop. Okay, so the initial magnetic flux is just going to be, well, I mean, let's write out the formula for flux again. So it's just the dot product between the area and the B field. So another way of writing that is BA cosine theta. Now we're gonna draw our area vector so that it's pointing in the same direction as the B field. So into the page. Okay, so I just drew my little area vector there. Um, and so the angle between them is 0. So cosine of 0 is 1. So like theta is 0, and so this just goes to 1. Okay, so this reduces down to just B times A. So the initial magnetic so the initial magnetic flux is just going to be B times D squared. Okay, so it's going to be like whatever the magnetic field strength is, which is 0.6 Tesla, times the area of the loop, and each of these is like a length of D. Okay, that's D, so D squared. Okay, so and then so you pull the loop completely out of the field, and the loop ends up like over here, like, right? Like, so, I mean, I'm just going to draw part of it because there's not enough room, but like the loop ends up over here. And there is no magnetic field, like the B field here is 0 because there's no little X's there, right? The B field is like constrained to this like one area in space. So the final flux, therefore, like if the B field, so it's like B times A, but B is 0, so this is just 0. Okay, so that's part one. Okay, so now we're going to use Faraday's law to find the induced EMF. Okay, so this is pretty straightforward because I know that Faraday's law just says that the change in magnetic flux over time is equal to the induced EMF or the voltage, right? And the negative sign gives me the direction that the current will be induced, like which direction does the induced current go based on that EMF, okay? So I can just write this out. So it's going to be, so this basically is lens. Okay, so I'm going to put the negative there. And then, so I'm going to subtract the final flux. It's like final minus initial, right? Divided by the time. Okay. Um, and so this is just going to be minus 0 minus B times D squared over delta T. Okay, and then I can plug the numbers in, but the negative sign and the negative sign gives me a positive sign. So that's going to be B D squared over delta T. And then if I substitute, I don't think I'm going to bother doing that right now, but like if you substitute the numbers in, like B is 0.6 Tesla, D is 0.05 meters, t is 0.1 seconds, then you'll get the answer. Okay, and that should be in volts, right? The answer should be like some number of volts. Okay, you can do that out yourself. Something to note is the positive indicates clockwise current, like the current should go clockwise. So let's just see if that makes sense using our like the same rationale that we did before. So the the flux is decreasing, right? And it's decreasing into the page, right? It's initially pointing into the page, and the flux is decreasing as I pull the loop outside the field. So the induced B field is going to also be, let me write this, B induced is also going to be into the page, right? And so I point my thumb into the page and my fingers rotate for the direction of the current, and that is indeed clockwise. Okay, so the current would go like this. Okay, does that make sense? So like again, let's just go through that rationale again. The external B field, which are these little blue crosses, are pointing into the page. The flux is decreasing because I'm pulling the loop outside, like it's getting smaller and smaller and smaller as the loop moves to the right. So Lenz's law says to oppose that change in flux, there is going to be an induced B field. So that induced B field has to also be pointing into the page to kind of counteract its change. And then last step, I point my thumb into the page, and then my fingers represent the current, which is indeed clockwise, which is indicated by this sign, clockwise. Okay, and negative would be counterclockwise. Now, I personally never use the sign. Okay, you can do it like you can do it like I just did it, right? Like I did the math and the sign told me positive and positive is clockwise. But I personally find it easier to reason through in the way that I showed you on the previous page than to rely on getting the sign right. Okay, I mean, it's up to you. You can do it either way. And I mean, it worked out the same in both cases, but it's just like for me, I like to use I like to use like the logic of like, is the flux, what's happening to the flux? Okay, based on the flux, what's happening to the, or how, which direction does the induced B field go? Based on that, which direction does the current go? Instead of relying on the sign that I get from the math. Anyway, that's just a piece of advice. So last question. If the loop of wire has a resistance of 100 ohms, calculate the magnitude and direction of the induced current. Okay, so we know that so we're given that the resistance of this wire is 100 ohms. And so we can just use, we can just use Ohm's law, right? So like, okay, so we know that Ohm's law, and there's a problem on the challenge that asks you to do this as well. So is V equals IR. We know that V is the same as the induced EMF. In fact, those have the exact same meaning. It's just two different words for the same thing. Okay. So I'm asked for the current. So the current is just going to be the EMF divided by R. Okay, and I know that the EMF, I just figured it out, is B times D squared divided by delta T times R, okay, from that part of the equation. And now I can just substitute in the numbers. So this is 6 Tesla, this is 0.05 meters, this is 0.1 seconds, and this is 100 ohms. And so I'm going to get a current of about 1.5 times 10 to the negative 4 amps. Okay, so that's, I think, gives you a good overview. To be honest, there's not very many different types of problems with Faraday's law and Lenz's law. It's kind of like once you've done like one or two, you've done them all. They all follow this very like specific pattern. And so I think that gives you a good idea of like Faraday's law, Lenz's law. Like I said, in the next video, I will go over a bunch of examples from the last two concepts in collage.